Okay, so this video is going to be getting into the Biot-Savart Law that was talked about in the previous overview. So I presented them like this. This is just the top half of the page from last time. But first of all, there's this cross product in here. I didn't mean to scare you away. This is a way to encapsulate the whole law all in one, just like over here with this special r hat vector. You can basically say that this electric field is going to be radial. But of course, most of the time we don't try to write these laws with the size and direction all kind of encapsulated. So let me just switch over and talk about how these laws, the way we normally talk about them, which is to say with size and direction separately. So here is the electric field piece. So we have a small contribution dq, which is going to make a small electric field contribution dE. And then over here, we kind of similarly have this contribution. This is kind of the heart of the Biot-Savart Law, IDL, and that's going to make a small contribution dB. So let me write these both out here. So here we have a little dq. So that's of course what we might call a point charge, an infinitesimal point charge. And the equivalent over here for the Biot-Savart Law is that I call it like a point current. Okay, so this is like a point charge. Infinitesimal point charge, and this is going to be what I'll call, it's sort of an analogy, point current. Okay, now it's not that the current is very small, but what it is, it's a very, very small segment of a wire. So there's a very small segment here that has current I going through it, but its length is really small. So this length is very short, so this is dl. And we can also give this a direction, so that we don't generally want to make current a vector. So instead what we do is we define a vector called dl with a vector hat. And dl with a vector hat is a small vector that points along the same direction as the current. So it gets its direction from the current, and it has a small length dl. So over here we have a point charge. Here I'll call this a point current in the sense that it's a very, very small segment with a current I. Now I do want to point out something interesting, is that this is just a number. So this is a scalar, which is just a number. But this thing over here, there is a vector nature to it. So it's not just something that is how much current, but there is a certain natural directionality to it. So that's going to have some bearing here in just a moment. Now over here, as far as direction goes, we know that, let's say this is a positive dq, it's always radial, and if it's outwards, it's outward if it's a positive charge, so it'll look like this. So this is the way the electric field looks. It goes radially outward in all directions. And if we were to plot that, so dE versus R, if I went out in any given direction, let's say this one, of course we have this inverse square law that we oftentimes see, and what that means is that this electric field that this is contributing is going to drop off with distance as 1 over r squared. And if you look over here, this is exactly the same. So if we go off in some random direction, let's say this way, we will find that the magnetic field contributed along that direction does die off as 1 over r squared. They're both inverse square laws. Okay. The other similarities, of course, there's some constants in the front. Here's k, and then here's some constants in the front here as well. And you might wonder why is there a separate 4 pi outside? Why don't we just absorb the 4 pi into that constant? I don't want to get into that. There's good reason for that, but essentially think of this as just a constant in the front. So if you look, the two laws are very, very similar in all their elements. There's the dq here, the point charge. Here's the point current, the 1 over r squared, some constants in the front, and then this is dB and this is dE. So the one thing that really makes this stand out is, of course, this extra appendage, right? The sine of theta. That's something that is completely foreign to the electrical side that we now have to talk about on the Biot-Savart Law side. And so let me go ahead and talk about that. Now, dl we've already talked about. It has a direction, so it's there. This is just the magnitude of dl, but this is the magnitude. So dl, again, is a vector that points along, that points in the same direction as current. And r hat, right here, r hat is a unit vector that points from this point current, where that's actually making the field, over to where you actually want to know what's going on. In other words, you want to know what the magnetic field is over there. And so what you have to do, in order to know something about the magnetic field contributed, you need to take a look at the sine of the angle between dl and r. So in this case, dl points to the right and r hat points this way. So this angle is going to actually affect what is the magnetic field contributed here. So there is some angular dependence. If you look at these different angles, you will not see the same magnetic field contributed everywhere. Okay? In fact, it goes as the sine of the angle, which means that if we plotted dB versus theta, this is at a given r, at a fixed r value, it would look like this. It would look like a sine function. And I only need to draw it from 0 degrees to 180 degrees, of course, because that's the maximum angles that two vectors can make to each other. You put them tail to tail and you measure the largest angle between them, so that could only be 180 at most. So what that actually tells you is that at 0 degrees and 180 degrees, there is no field contribution. So if the angle between these two is 0, so in other words, dl points to the right and r hat points to the right as well, so that's because you're interested in over here, that means that there is 0 field, okay? So along the line ahead of the point current, there is actually 0 field contributed here, and likewise, if you're somewhere behind this, and the angle between dl and r hat, which points to where you're interested in knowing the field, if that's 180, it's also 0. So along the line that the current kind of makes, so that is defined by this point current, there's actually 0 field. And then likewise, if you go off at 90 degrees over here, that is actually where you get the maximum contribution. So if you went off over here somewhere, this would be actually the maximum field strength. And likewise down here as well. So along a line that runs perpendicular to the current, you actually get maximum field. So this is, of course, completely alien over here, no matter what angle I'm at. So if I'm going over here, it doesn't matter what angle I am around this thing, I'm going to see exactly the same field strength. So if I were to draw the equivalent diagram, dE versus theta, at a given r, so at a fixed r value, of course, there is no dependence here. That wasn't a thing that happened before. And it sort of makes sense because this is a scalar. So this is just a number, so directionality doesn't really enter into it. Of course, no matter if you're 1 meter away on this side or this side or this side, you're seeing exactly the same thing. But if you are over here, of course, and try to draw this circle here, I'm going to run out of room, but if I were going around at a fixed distance around here, of course, sometimes I'd see, this is a vector, so sometimes I see the current going like this, so kind of not pointing toward me at all. Sometimes I'd see it pointing toward me. Sometimes, again, it would be not at all pointing toward me. So because this is a vector, that's what gives rise to the fact that not everything's the same. When you're a given distance away, that's not the end-all be-all. It also matters how the current is pointing relative to where you are. And so that's that extra term that comes about from the fact that this point current is a vector, whereas this point charge here is not. It's a scalar. And so that's kind of the new aspect. So this part, just the distance dependence, this is exactly the same. The only thing, of course, you have to say here is that this magnetic field contribution dies off with distance if it's not 0 all the time. So this graph would only be good if it's not 0 degrees or it's not 180 degrees, because if you're going off 0 degrees or 180 degrees, the field is just flat at 0, right? The field contribution would just be like this all the whole way. Let's go ahead and draw this in, though I guess the one thing I do need to fill in is tell you a little bit about how to get the direction of this. Now, if those of you that are comfortable with the cross product, of course it comes from the cross product DL and R hat, but let me tell you there's a shortcut to do this, and that's another right-hand rule. It's another use of right-hand rule number 2, the curly straighty one. So point your fingers along I, and your thumb along I. Excuse me. Your thumb goes with I. That's the straight thing. And your fingers will give the wrap of the magnetic field. So that's the curly thing. That's the curly straighty is right-hand rule number 2. It's pretty much what you already saw in the other videos in terms of longer currents, so it's just basically the same thing. So I point my thumb along the current, thumb of my right hand, and the magnetic field is going to wrap around it like this. So it's going to be above it, it's going to point out of the page, and below inward. So let me go ahead and draw it like this. So out here it's out of the page, over here it's into the page. And since we said it was maximum going out at 90 degrees to the current, let's draw it getting smaller here. It's going to get smaller and smaller and smaller, and then when it crosses this line, it's 0, right? We said it was 0 along the field, along the line ahead and behind the charge, and then when you cross over that, it gets to be point in the other direction. So now it's inward, 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 until it becomes maximum again over here, and then smaller and smaller, and again crossing here, it's 0, and then it points out, getting bigger. So that's basically what the field lines look like. They wrap around this current. They have the maximum size 90 degrees to the to where the current points, and then along the line that the current sort of defines, there's actually 0 field throughout. So that's the essence of the theory of what it's saying. It's essentially very similar, except for this sign part. That's the unusual part. And what we'll do next is actually use this to integrate a couple of actual wires. This is just an infinitesimal point current, so we're going to need to actually integrate and make some wires out of this.